everybody. In this video, we're going to talk about finding an infinite geometric series. So just remember that a series is a sum of a sequence. It is a sum of a sequence. So this is really getting tricky. Sum of a sequence. This is really getting tricky because we're talking about an infinite series. That means a series that goes on and on and on and on forever and ever and ever. So it's crazy that it could have a sum if it continues on and on and on forever. So let's chat this through. We've got a couple examples here for you to kind of break down what's happening in these different sequences. So here's my first sequence. You can notice that it's getting smaller and smaller and smaller with each iteration. In fact, we're dividing by 2 over and over and over again, and the fraction's getting teeny, teeny, tiny. So if I find the sum of just the first term, well, that's a freebie. That's just a half, okay? The sum of the first 2 terms would be 1/2 plus 1/4. And I've already put that into a calculator for myself, so I don't have to do that while I'm talking with you. 1/2 plus 1/4 is 0.75. Okay, the sum of the first 3 terms would be 1/2 plus 1/4 plus 1/8. Already done that. 1/2 plus 1/4 plus 1/8 is that last part you see there, 0.875. So I can keep using a calculator to generate these sums for me. So I'm just going to finish filling this in. The first 4 terms would be 1/2 plus 1/4 plus 1/8 plus 1/16. So now we're at 0.9375. All right, so what's the next term in the sequence? If I keep going, dividing by 2, the next term is 1/32. So if I add those 5 terms together, now I'm at 0.96875. The next term in my sequence, half of this would be 1/64th, getting smaller and smaller and smaller. So I'm just adding this teeny tiny value each time. So the further and further I go, I'm just adding something so teeny, teeny, tiny, and that's going to get infinitely smaller. So you can see where this is moving towards. The sum of this sequence, if I continue adding, is getting closer and closer to 1. It has a definite ending that it's getting to. So even though it's an infinite sequence, when I add all of those infinite parts together, the sum is getting closer and closer and closer to 1. You guys, that is called a convergent series. A series that approaches a certain sum, a sum that you can absolutely find, that is called a convergent series. All right, let's compare it to this next example. Take a look at this sequence. I start with 1/2, and then it goes to 1, 2, 4, 8. So it's growing, and this time I'm multiplying by 2 every time. So again, the first sum is a give me. The sum of 1/2 is just 0.5 if you want to write it as a decimal. The sum of 1/2 plus 1 is 1.5 or 1.5. The sum of the first 3, that's 1/2 plus 1 plus 2. Well, 1 plus 2 is 3, and 3 plus 1/2 is 3.5. So we can do these in our head. The sum of the first 4, that is 1/2 plus 1 plus 2 plus 4. 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 1/2 is 7.5. And on and on and on, okay? So let's see. 5 terms. That's all 5 of these terms added together. That would be 15.5. What would our next term in the sequence be? Well, I'm doubling every time, so our next term is 16. So if I add all 6 terms together, now I'm at 31.5. So what happens as this sequence keeps growing and growing and growing, and we keep adding more and more and more on, this sequence just goes to infinity. The sum of this sequence as it keeps growing and growing and growing is infinity. It does not have a certain sum. It just gets bigger and bigger and bigger, and that is called a divergent series. So we're comparing two types of different geometric series. A convergent series is one that approaches a specific term, a specific sum, whereas divergent series is one that does not approach a specific sum. Well, one way that you can tell the difference in these are the R values. So let's go back over here and check out this R value. For each term, I'm dividing by 2 each time. Divide by 2, it's getting half as big each time. So this R value is a half. So if our R value is less than 1, I guess I should say the absolute value of that R value is less than 1 because it could be the same with a negative 1/2. If the R value is less than 1, that will always be a convergent series. In our second example, my series grows, it doubles each time, so my R value is 2. And you all, when your R value is greater than 2, then that is called a divergent series. So these infinite geometric series go on forever and ever and ever and ever. It's all about the R value as to whether or not we'll be able to find that sum or not. Okay. All right, so for convergent series, that's the one we're interested in because we want to know the sum of the series, right? So if we don't have a sum, meaning if it's a divergent series, we don't need to waste our time with those type of problems. We want to find the sum. So here's a formula for the sum of a convergent series. Jot that down carefully. It is on your formula sheet. Okay, the sum of a convergent series is the first term, a sub 1, times 1 over 1 minus r. Okay, so step 1 is going to be find the r value. Let's decide if it's convergent or not. If it is convergent, we'll continue with this formula to find the sum. All right, so let's see. Let's see if we can figure out the r value. What's happening as we go from 1 to a 4th, or 1/4 to a 16th, or 1/16 to a 64th? Well, with every iteration, we are dividing by 4. So that means our R value is 1/4. 1/4 is less than 1, so this is a convergent series, which means we will be able to find a sum. So now I'm going to use this formula to find that sum. This is an infinite series, so our n value is infinite. Our first term is 1, and our R value is 1/4. All right, you know me. I'm going to take this over to Desmos to help me with this math. So let's get on over here to Desmos. Okay, it's 1 times, hit your fraction button or your divide button to build a fraction bar. 1 over 1 minus 1/4. Fractions in fractions. Check that out. And we get a final sum of 1.3 repeating, or you could write that as 4 over 3. Okay, so a lot of steps here, a lot of things to think about. If we need to write down some steps, we can. I would say first things first is find the R value. Then decide, is it convergent or is it divergent? If it's convergent, then go use your formula to find the sum of the series. Okay, so maybe those are some good steps to follow if you're feeling a little overwhelmed. All right, take a look at number 10. We're going to start with step 1. Find the R value. Ooh, this is a yucky one. How do we get from 2/3 to 8/3, or 8/3 to 4/3, or 32/3 to 128/3? Notice the 3's are all the same each time, so maybe we can just focus in on the numerator. To get from 2 to 8, I multiply by 4. From 8 to 32, I multiply by 4. From 32 to 128, I multiply by 4. So here the R value is 4. All right. Check this out. If you have an R value that's greater than 1, that is a divergent series. So this is divergent, which means its sum is not specific. So we don't need to continue with this problem. Okay, let's try number 11. Ooh, number 11 looks icky. I have to start with finding the R value, and that is a mess. So if you ever have trouble finding the R value, you can again use Desmos and take any term and divide it by its previous term. So like if I take 3.48 and I divide it by 5.8, that'll give me my R value. So my R value is 0.06 or 0.6. That means I am multiplying each term by 0.6 to build the new term. And you can check that. 5.8 times 0.6 get you 3.48. 3.48 times 0.6 get you 2.088, which is what's building our series. So our R value is multiplying by 0.6 each time. Okay, if our R value is 0.6, that is convergent because 0.6 is less than 1, which means I can find a sum. So now I'm going to go over to my formula. The sum of this infinite series starts with 5.8, and we multiply that by 1 over 1 minus the R value.
Megan Plott, please call extension 5771. Megan Plott, call 5771.
Okay, so I'm over in Desmos. I've got 5.8. Get my fraction bar set up. 1 over 1 minus the R value of 0.6. And I get a final sum of 14.5. Okay, guys, let's talk about a series that goes to infinity. If you have been relying on summation here, you're going to have to be very careful if you've been relying on the sigma, because there is no way to input infinity into the sigma notation. Okay, so I'm going to pull out some of the, first I'm going to work this with the formula that we're currently working on, because that's always a backup plan. So let's identify some of the pieces here. I need the first term, so I need an a sub 1. So what I'm going to do is plug a 1 in for x. Well, hold up, before I even do that, I should figure out if this is convergent or divergent first. So that's really important. Well, right here's my R value. My R value is 1/4. So this is a convergent series. So I do need to find the sum. Okay. So I'm going to find the sum of the infinite series. Okay. My first term is -2. And I'm getting that from right here, everybody. Or you could even go back to your geometric sequence, where we started with a sub 1 times the R value to n minus 1. Okay, so my first term here is -2 times 1 over 1 minus the R value of 1/4. So we're using both formulas at the same time here. We're using this one to recognize where the common ratio and where the first term is. and then we're plugging those into the series formula. Okay. You guys, I'm trusting at this point that you can get this entered into Desmos. So I think this is the last time I'm going to show you how to enter these values into Desmos, because I think you can do that. So this would go -2 times, get our fraction, 1/1 minus 1/4. Fraction in a fraction. I'm getting -2.6 repeating. Okay. All right, so I want to talk about what this looks like in summation notation because we have no way of putting infinity into Desmos. So let me show you what happens here. Over in our functions, grab that sigma notation, and we're supposed to go from 1 to infinity. Now, change that to an x. I don't have an infinity, so what if I just put a really big number in here? I'm going to start with 100. Okay, put my formula is -2 times 1/4 to the power of x minus 1. That made it crazy looking. I think I got to put my 1/4 in parentheses too. Okay, check that out. I don't have infinity in here. I can't put infinity in here. So I put in 100, I could put in 1,000, and Desmos can still handle the calculation. What about 10,000? Desmos can handle the calculation. What about 100,000? At some point, Desmos might cut out at me because it can't hold the memory. This must not be a terrible function. So I've got a giant value in here, and Desmos can still handle it. You will run into some functions where Desmos may not be able to handle the idea of infinity. So you're just going to have to load up with some giant number and find Desmos's, find what Desmos can handle, okay? Okay, we're going to do one more together, and then you're going to get some time to study. So let's check out number 15. All right, this is written where our a sub 1 is 8, and our r value is -5/2. Well, guys, that means it's a divergent series, because -5/2, the absolute value of that is 2.5 if you put it in decimal mode, right? And 2.5 is bigger than 1, so that is divergent. So we're not interested in finding this sum. In fact, you can't find this sum. This sum is not specific, okay? Okay, I'm going to stop the video. Again, let me give you the answers to the evens over here so you can keep working. Answer to 12, 14, and 16. Okay, so keep working. Check your answers as you go. And happy studying. Look back for a video on more practice if you need to.